remember, when you have that dry cow, there are three generations represented: the cow, the daughter, and the granddaughter. And if they are under heat stress during that relatively short period of time of 45 to 60 days during their dry period, you can have a downstream effect in those three generations.
Welcome back, everyone, to the Dairy Science Digest. This is a podcast designed to bring the Journal of Dairy Science straight to the ears of dairy producers. I'm Reagan Bluel from the University of Missouri Dairy Team, and we're just marching right into the hottest time of the year, so I can't think of a better time to talk to Dr. Laporta from the University of Wisconsin about her team's recently released articles. Now, that's plural. There are 2 articles in this month's Journal of Dairy Science Articles and Press list from this team, which is a continuation of a project that started many years ago. In fact, if you guys want to look back at the clickable links at the bottom of the show article, I featured some of this original research way back in July of 2020. And what we're focused in on is the heat stress effects on the unborn fetus. So listen up. This is not just another podcast telling you to cool your cows through the summer heat. This month, we're really zooming in to the physiological changes that occur inside those baby calves that are incubated like a crock pot inside that hot dam. So let's head forward and continue to learn from this cohort of Florida cows that were exposed to heat stress. Dr. Laporta, could you tell us a little bit about how you're in Wisconsin, but talking about Florida cows?
Well, first of all, thank you for having me and for featuring our latest research that really starts several years ago, as you mentioned. I started this line of research in Florida when I started my research position there in 2015. I started collaborating heavily with Dr. Jeffrey Dahl there. He did a lot of work in the dry cow heat stress model. So I really jumped in and took advantage of that and started looking at the fetal programming effects on, I really like your analogy that you use that are cooking a crock pot. I'm going to start using that from now on. So thank you. Because that's really what it is. When we think about that dry cow, there's also that fetus that is growing inside her, and that late gestation that coincides with the dry period. It's really a period of a lot of changes, physiological changes and metabolic changes, and there's a lot of epigenetic changes that are happening, and heat stress is really taking a toll on those heifers. So I started in Florida, clearly the epicenter of heat stress. So my background was more physiological, mammary lactation physiology. So I took this opportunity to look into the effects of in utero heat stress on fetal programming of the mammary gland. And this took on, we started looking at many other tissues. My focus has always been the mammary gland, but we have seen that in utero heat stress really takes a toll holistically in the animal.
Yeah.
So we have expanded to many other tissues, such as the adrenal gland that you mentioned in one of these feature articles in JDS.
I want to focus in a little more on the mammary gland, but before we get there, we really got to maybe talk about it, the 30,000 foot. When I'm talking about the effects of heat stress, quoting all of your articles over time, I remind these guys that the heat stressed animals, they still had access to shade. They still had access to a barn. And so could you talk a little bit about that foundational research project and explain the difference between heat stress versus cooled dry cows?
Absolutely. So the model that we use in Florida is multiparous cows that are under a freestall barn with access to shade. So those are our heat stress cows. That's our control cows. And it's just the heat stress of Florida. Obviously, very hot and humid, even during night. So those animals have really no time to get rid of that heat. So those heat stress cows that are pregnant are under chronic heat stress for the entire duration of their dry period, which we target at 49 days, give or take. And the cooled animals, as we refer to those, they are in the same barn, but we provide water soakers and fans, so a combination of both. And when temperature hits 7 degrees, then these are activated, those soakers, and they go in a cycle, just a very typical for Florida. So shade, fans, and soakers. So what we're trying to do there is to bring back these animals to thermoneutrality, which is when they do really well. As we all know, cows do better in the colder weather.
Sure.
And so the terminology that we use, cooling, it's just bringing them back to where they need to be, right? So that
Absolutely.
they can dissipate heat effectively and put that energy into their mammary glands to make colostrum and in that fetus in preparation for parturition.
And for those of you listeners that are kind of new to the idea of heat stress, I will do a clickable link about the THI index. And so that's really taking into consideration the temperature and humidity, like Dr. Laporta was talking about, because boy, if you're in a dry climate, then perhaps those temperatures aren't as impactful. But we know here in Southwest Missouri that humidity definitely impacts cows. And I applaud the work that's going in, that's kind of setting the stage. And as you referred, they're being incubated for about 60 days, and then they give birth. And that first animal is what we call the F1 cross.
Yep.
And so that is the daughter of the heat stress dam. But this article that we're talking about in the mammary gland is actually talking about the F2. So can you talk about the management of that F1 calf, and then how did you get the F2 calf?
Right. Yes. So you explained it really well. So these F1s, so it's the first generation of those mothers, as I will refer to, which are the F0. So the generation 0, that was the one that was heat stressed directly or cooled directly. The daughters that were in utero, heat stress or cooled. We follow these daughters, F1s, for many years, and we generate the granddaughters of the dry cow, okay, to the F1s 2 years after. And so we have the F0, which is the dry cow herself. We have the F1, which is her daughter, who was in utero heat stress. And then we have the F2, which is the daughters of the daughters, so the granddaughters of that cow. It's a mouthful, but the link between the granddaughter and the granddam is that in the fetal daughter, so the F1, when she is in utero, her ovaries have all the eggs that are going to be ovulated in her lifetime. So during these 45 to 60 days of heat stress in utero, we're also impacting those eggs that are going to generate the F2 2 years after. Wow. So what we think is happening, there's a residual effect in these ovaries, and we have a paper that it's in preparation now. So maybe in a while we can talk about that. But the ovaries of these daughters are smaller, and they have compromised ability to ovulate. And so we're having a carryover effects that it's passed on to the second generation or F2s. So we see that these F2s also produce less milk, they survive less. We see a lot of early life losses in those F2s. And this is what we started in that 2020 podcast that you presented the link earlier on. So yes, this is a trying to understand why these things happen. And we were able to get our hands on to the F2, so the granddaughters. So we looked into their mammary glands and see what was going on there.
It's so impressive. And spoiler alert, guys, there's a link to this specific paper of carryover effects of maternal late gestation heat stress on granddaughters' growth and mammary gland development. And boy, if you're not driving down the road right now, you need to pause and click on that link and check out the histology. There's some beautiful photographs of what's happening inside the mammary gland of these F2 calves that are several years in the making, right? If we could just pause and let's just applaud the Land Grant University for taking the time, right? I mean, so here we have these Land Grant universities that are, I mean, if we start doing the math, this is 7-8 years in the making, right? In order to get this data set. But because we are so committed to the science of advancing the dairy industry forward collectively, that's how we were able to do this. And I can't wait to tell the story.
I wanna make a comment on that commitment, because we talk about, I'm currently at the University of Wisconsin Madison, so along the way in these long-term studies that we do, I was recruited back to University of Wisconsin. I did my PhD here, so I came back to Wisconsin, and I took 40 heifers, actually. They were 2 months old, so I drove them. I didn't drive them myself, but I did drive with my students and my samples all the way from Florida to Wisconsin. But a point to mention here that it's important, I think, for producers and for the industry in general, is that these F1s, so the daughters, were moved across the country when they were 2 months old. So they came to Wisconsin in the middle of the winter. They went through 2-3 winters and summers all together as a cohort with those that were in utero cool. And those are the ones that generated the F2s, the granddaughters. The take home here is that no matter what you do, where you go, those effects that happen in utero,
you can't fix it.
Remain. And, some of the research now is trying to understand why this happens and if we can fix it.
Yeah.
But probably we need 8 or 10 more years for that.
Right. Very good. Well, okay. So I think you bring up a good point, because that's always a question that's asked, is how they were managed. And so all of them went up to Wisconsin. They were not heat stressed. They did not go through the same rigorous study of fans, coolers. They were all managed the same as one cohort.
Yes.
So let's dive right into that mammary gland. You were taking biopsies of, first ultrasounds and then biopsies, focused in on the fat pad and the parenchyma. Just guys, this is kind of, parenchyma is the productive tissue, and you want to describe a little bit more about what those tissues are and what you were looking for in those samples.
Yep. I wanna take a step back a little bit to just tell you that in the F1s, so the daughters, we have 2 or 3 publications showing that their mammary glands is greatly impacted. So we did a series of euthanasias and biopsies along the lifetime. So the F1, birth, at weaning, at puberty, during lactation, and we see these detrimental effects in their size, in their microstructure, and that results in the F1 producing less milk in their first, second, and third lactations. So that took us to the F2s.
Wait. Okay, say that one more time. So not only did their first lactation get compromised, but their second and their third lactation. So they're damaged goods, guys. Damaged goods. Okay, sorry to interrupt, but when I saw that graphic, you have a publication that I'll also link at the bottom. There's going to be tons of links this month, but the publication that summarizes the total milk loss over this generation, I mean, it destroys cow families. It really does. Okay, so back to parenchyma and fat.
Yes, so then we wanted to see if those detriments that we see in production of the F2s and survival were due to the mammary gland microstructure and gene expression and things like that. So I'm a mammary physiologist by training, so I really enjoy looking into their tissues and genes and proteins and things that are being expressed that we typically don't see. And so for these F2s, these granddaughters, we follow them from birth until 2 months of age. So we took a lot of measurements: growth, average daily gain, feed intake. We took microstructure measurements of their mammary glands. So bottom line here, phenotypically, they are identical. We didn't see any differences between those F2s that were born from in utero cool mothers, F2s that were born to in utero heat stress mothers. So they look identical, and that's a problem,
tricky.
right?
Yeah, that's tricky.
Yes, that's a problem because,
you're trucking right along. You think they're fine, right? You're throwing all of this money to them.
Yeah, we see more phenotypical difference that might indicate, they're smaller, they are born smaller, they stay smaller. But with the F2s, we didn't see any of that. But at 2 months of age, after they are weaned, we did mammary ultrasounds, we did a biopsy, we look at their skin, sweat glands. That's another publication, but we can talk about that another day. But for the mammary gland, what we see is that parenchyma, that is what would become the secretory structure that is going to invade that fat pad, is smaller in those F2s that were born to in utero heat stress mothers.
Wow.
And so they start off with less tissue that is going to grow into as the animal ages. And one point to mention is that early mammary growth and how stressors, obviously heat stress being a big one, can really derail that mammary growth early in life, and that can really have effects later on. We typically tend to look at the mammary gland, when they reach puberty, and then during gestation a little bit, and then obviously when they are making milk. But what happens before is really important in that developmental plasticity of the gland. So in these F2s, we see that they start off with less potential. So what we see is that parenchyma tissue is smaller, and also the fat pad is smaller. So what's going to happen is the parenchyma is going to grow into that fat pad and start to proliferate as the animal ages. They go through puberty. Then what we think is happening is that they go on to produce less milk. The parenchyma also proliferate less. So we look at a marker of cellular proliferation, which is how cells divide and grow. And we see that those F2s born to in utero heat stress F1s have less proliferation, have less estrogen receptor, which we know it's important for mammary growth. And so all of these indications are leading towards a less responsive mammary gland, a smaller mammary gland that will respond less to estrogen when they reach puberty.
Boy, when I was looking at the histological slides that are presented here in this paper, focused in on the luminal versus non-luminal, you can visually see the consolidation of that mammary tissue, guys. And so lumen, of course, is going to be like the balloon that as she is producing milk out of those epithelial cells, secretory cells, they drip into the lumen, and that lumen expands like a water balloon. If they have more non-luminal space, that means less space for that milk to be held. And it's just, if she has less water balloon holding capacity, she's never going to produce as much milk. And we've been documenting that mathematically through observations and data in your previous papers. But here we can actually physically see it on the histological slide. And when you quantified it, it is in fact statistically different. You want to talk a little bit about some of the statistical differences that you found in the mammary tissue?
Yes, what we see is less luminal and non-luminal epithelial structures, as you described. And this is important because obviously this is a two-dimensional structure, but in reality it's a three-dimensional, right? But what we see here is you can think of it as finger-like projections that are going to invade the fat pad. And so what we see is that the F2s that are born to cool mothers in utero, what they have is a lot more finger-like projections. So a lot more ducts are invading that fat pad. Clearly, this is an early mammary gland, so it's not actively producing milk like you would think for a mature cow. But these structures are the ones that are going to be doing that in the future. So what we see here is statistically significant more cells that are proliferating. So we have this marker, KX67, that we see those F2s have a lot more of that. And they also have a lot more estrogen receptor, significantly more. And so what that indicates is that these mammary glands are going to be more responsive to estrogen, and they're going to be proliferating more. So what we think that's happening is that when they reach puberty, they're going to be growing more than the ones that are born to in utero heat stress F1s.
Man, incredible.
So I think one important thing to recap here in terms of the mammary gland is that in that dry pregnant cow that it's under heat stress, there are 3 generations that are represented. So the cow herself, who's the F0, and we see that in her next lactation, she produces less milk, but her mammary gland, it's also the microstructure and the molecular signature of her mammary gland is impaired as well, and they produce less milk.
Good point.
Now, the F1, so the fetal daughter, we see all of these changes in their mammary gland, in their size, in their microstructure, macrostructure all along the way until their first, second, and third lactations. And now we're seeing these effects still remain in that F2, which is striking. So remember, when you have that dry cow, there are 3 generations represented: the cow, the daughter, and the granddaughter. And if they are under heat stress during that relatively short period of time of 45 to 60 days during their dry period, you can have an effect, a downstream effect in those 3 generations. Clearly, this Florida heat stress is chronic, so we have to think about that as well. But I like to think about that dry cow representing 3 generations and start taking a little better care of her.
Absolutely. Yeah. Pretty incredible. And a question kind of sort of on the top of mind right now. I wonder if someone were to ask you in an extension type role, I'm going to go build a new barn. Which is more important? Should I build a barn for my dry cows or my lactating herd?
A tricky question.
Yeah, right.
I don't think we're going to reach a consensus on that. I think that obviously lactating cows are impacting the bottom line directly, right? So heat stress really takes a toll on them, and they can reduce production up to 40% depending on how detrimental that heat stress is. So I think it's important to cool your lactating cows from obvious standpoints, but also keeping in mind that that dry cow can really carry over through 3 generations. That's really impactful as well. When you look at the economic impact, the estimation of the economic impact, at least the first and second generation, the cow herself and the production losses of their daughters. We haven't estimated the F2s yet because, this is just starting. So we need to generate more solid data on this. But if you look at lactation and of her daughter in her first, second, and third lactation, and you factor in those reduced productive life that F1 has, right, the economic impact can really be very close to what we estimate for lactating cows. That doesn't mean it's more or less important. I think both are, and it's hard to take sides here. So I think it's more of a holistic view to heat stress affecting not just the lactating cows, but also non-lactating cows.
You bet. Absolutely. And I'll put a clickable link to that article too, because it was really impressive how you guys looked at the economics based on where you're at in the nation and how many heat stress days you anticipate having and the number of cows present in the state. But lots and lots and lots of really great information coming from these F1s down in Florida. So let's shift gears a little bit on the adrenal gland. First and foremost, can you do just a broad sweep? Why do we care about the adrenal?
Yes, absolutely. This is one of the things that I mentioned earlier that, our focus has been the mammary gland, but obviously heat stress affects the animal as a whole. And so the adrenal gland came about because the adrenal respond to stress, right? And it's divided into different areas that we can say very briefly: the cortex, which is the outer portion, and the adrenal medulla, which is the inner portion. So the adrenal gland, some of these hormones help in really a lot of biological functions, you name it, metabolism, blood pressure, but one of them is the response to stress. So this is not novel in general. Like, this research started in the 30s with the father of the hypothalamic pituitary axis and cortisol and stress in the 30s. So they showed in rats that any type of stressors can really affect the size and the functionality of the adrenal gland. So our hypothesis was, okay, so if these daughters, if these F1s are heat stress in utero, how are their adrenal glands impacted? So you would expect that they are stressed, they're going to produce more cortisol, which is one of the hormones that is secreted by the adrenal gland. And so we wanted to look at this. So we euthanize animals at birth and at weaning, and we look at their adrenal glands. Bottom line, what we found was that particularly at weaning, those adrenal glands, the gross weight of that adrenal gland was larger. So we see this enlargement in the adrenal glands of in utero heat stress F1s, so those daughters. So they were inflamed, they were larger. and particularly at weaning. So we think that the combination of the stress of weaning with that adrenal gland that comes already impacted by in utero heat stress, so the ability of that heifer to respond to another stressor can be impacted by that previous exposure to in utero heat stress. So what we see is that it's not only larger, but all these zones that I mentioned that secrete different hormones, one of them being cortisol, but there's also adrenaline and some estrogen as well, created by the adrenal. So all the zones that we assess in the adrenal gland, the zona glomerulosa, fasciculata, and reticularis that secrete all these different hormones are thicker, are larger in the in utero heat stress daughters. So the zona glomerulosa is the one that makes cortisol. We always associate stress with cortisol. And what we see is that zone, that specific zone, has more cells per area of tissue, and those cells are larger. So in the in utero stress, so
all of a sudden your wheels are just turning, right? This paper, I think, is going to be pivotal, referenced time and time again in future research, because the first thing that I want to say is, how does this impact the animal? And while we don't necessarily know directly out of this particular paper, it produces a foundation to then investigate so many other responses, because this adrenal is responsible for so much hormonal control. And it makes you wonder, okay, so those heat stressed animals and their intake, how do they go off feed more during the dry period, as they transition in, or are they more stressed as they transition to new groups? And how do they respond to those group transitions in the lactating barn and even within the heifer barn? I mean, my wheels are turning about all the different possibilities.
Yeah. So I think the bottom line here is that relatively short period of in utero heat stress can really derail that adrenal gland function. And we look at early life, but I'm sure that this has effects that carry over, like we see in the mammary gland, and how the animal adapt to other stressors or changes, like you mentioned. So I think this is important to think about as we think of stress. And we delve into heat stress, but the adrenal gland is a common factor for many other stressors. And we don't often talk about that as an industry, and we don't know how other stressors might impact these tissues. We focus mostly on heat stress, but in other species, they have shown that the adrenal gland responds to different stressors. So I'm sure it's a sum
complex.
Yes, it's very complex. Yeah.
Yeah. What about inflammation and the stress of inflammation? Does the adrenal have an impact on inflammation?
Yes, and we don't always think about it as the adrenal gland as an immune organ or a secretory organ like it really is, but we did take a piece of the adrenal gland, and we see that there are many pathways that are involved in immune function and inflammation. We see interleukins 6, 13, 17, a lot of immune-related pathways that are activated by that in utero heat stress. So the adrenal gland is really responsive to this. See immune cell maturation, Th1, Th2 activation, granulocytes, you name it. It's a lot to hone in, but the bottom line is that the adrenal is more than just a stress organ. It also can act as an immune organ and respond to inflammation as well. So we see that in this paper, in this publication.
You bet. And just like with the mammary gland, you can pull up the publication with the clickable link at the bottom and see the histological changes that are occurring to that gland. It's visually evident, additionally to the data that you guys measured. So if you were to summarize these two papers up into one big statement, what would you really like boots on the ground dairy producers to gain from this phase of this very informative topic?
I think if we think of those F2s that publication features, that dry period, heat stress period that is relatively short can really have an effect years down the road, not only in the daughters, but also the granddaughters. And I'm sure that if we start looking at other tissues in those granddaughters, we might see also a detrimental effect of that in utero heat stress as well. The mammary gland is the one that I have my heart very close to. So I think it's like you said, evident of these structural changes in the tissue that we see only if we are able to take a biopsy and look at these things. But from the phenotypic standpoint, those animals go under the radar. They look identical.
Tricky.
We can't tell where they're coming from. And really, this brings that question mark into the story. What's going inside that animal, and fetal programming is really what's going on here, right? And I think for the adrenal gland story is heat stress can impact many things. The adrenal gland is one that is closely related to stress because of its active secretion of cortisol. But again, seeing these structural changes in the tissue structure, hypertrophy and hyperplasia. We did a lot of that in this publication. It's striking to see that this relatively short period of in utero heat stress can cause all these detrimental effects in the animal that can affect them and manifest later in life on how they respond to stressors or how effectively they can make milk 2-3 years down the road. So early life management is important. That perinatal period, not only the in utero portion, but also those first months of life. That's another arm of our research program that we're looking into and doing more projects now. That pre-weaning phase, the animal is still developing, the animal is still plastic. And so we have an opportunity there to manipulate positively by removing stressors and have them do what they do best, which is, grow and make milk.
Oh, this is fantastic. Well, Dr. Laporta, I want to congratulate you on a set of fabulous papers and really helping the dairy producer move forward in times of heat stress and understanding the possible financial implications of how they manage these 60 days. And I want to thank you for your time. And listeners, I applaud you for taking time out of your day today to really better understand the lasting impacts of your dry cow management decisions on the success of your subsequent herd. I've really enjoyed our conversation. This has been the May edition of the Dairy Science Digest, a monthly podcast project designed to bring the Journal of Dairy Science straight to your ears. We highlight peer-reviewed research articles that are actively in press. It's sound science that you can base your management decisions around, provided by your University of Missouri Dairy team. So please be sure to like, share, and subscribe to get future editions straight to your cell phone. This is Reagan Bluel with the Dairy Science Digest, and I hope you have a great day.